Hello, discrete math fans. Now we're going to talk about mathematical induction. This is one of the cornerstones of mathematical proof. Now earlier on we talked about the Chicken McNuggets problem, and we asked what quantities of Chicken McNuggets that we could purchase if we only allowed boxes of size 6, 9, and 20. And we guessed, and we did this using our Python program, that the largest quantity that could not be purchased is 43. That means that any larger quantity could be purchased. Now it's not that hard to show that 43 can't be purchased. You could do this with a proof by exhaustion and just try all possibilities of lumping together 6s, 9s, and 20s, and you'll never be able to get 43. What's more difficult is showing that all larger quantities can be purchased. Now, in order to accomplish this, let's just consider a simplified problem. So here, the problem is that the McNugget boxes are sold in quantities of 3s and 5s. Now, it's pretty easy to see that we can't buy 7 McNuggets. There's no way of combining 3s and 5s to get 7. But as it turns out, we can buy any larger quantity. 8 or more can be purchased. We're going to prove that now, and our method of proof is going to be induction. So the basic idea is that if we have a few boxes of McNuggets that give us exactly n McNuggets, and here n has to be bigger than 8, we want to see if we can change our total to n plus 1. We're going to do this by swapping boxes around, changing the quantities of 3s and 5s that we have. But if we can always go from n to n plus 1, that means we have a way of going from n to any larger integer, and so that proves that any integer at all can be achieved with these small McNugget boxes. Again, we have to assume that n is bigger than or equal to 8 because it's not possible to get 7. Alright, so if we have a box of 5, we can always trade that in for 2 boxes of 3. That will increase your total by 1. On the other hand, if we don't have any boxes of 5, then we have to have lots of boxes of 3. And then we can trade 3 boxes of 3 for 2 boxes of 5. So that swaps 9 McNuggets for 10, so in that case you've also increased your total by 1. So either way, whether or not you have boxes of 5, there's always a way to increase the total by exactly 1. Alright, so the structure of our argument is going to go like this. Let's define P of n to be this predicate. Exactly n Chicken McNuggets can be purchased using only boxes of size 3 and 5. So then what we want to do is try to prove that P of n is true for all integers n greater than or equal to 8. What we're going to do is prove 2 things. First, we're going to show that P of 8 is true. Then, we're going to show that the truth of P of k plus 1 follows necessarily from the truth of P of k for each k greater than or equal to 8. So the idea is that you can always step from one spot to the next, no matter where you're at. So any argument of this form is called an argument by mathematical induction. So here's the theorem. It's the principle of mathematical induction. And it says that if we let P of n be a predicate that's defined for integers n, and we let a be a fixed integer, we're going to suppose the following 2 things are true. P of a is true, and for all integers k that are bigger than or equal to a, if P of k is true, then P of k plus 1 is true. The conclusion of the principle of mathematical induction is that P of n is true for all n bigger than or equal to a. Now, the validity of the principle of mathematical induction is often accepted as an axiom, a basic truth about mathematics that we don't prove. Now, in this class, we're actually going to prove it from what I'll consider a more basic axiom, which is called the well-ordering principle. We'll get to that soon. Let's go ahead and outline the method of proof by mathematical induction. So, in general, mathematical induction is a method for proving that a property that's defined for some integers n is true for all n that are greater than or equal to some initial integer. So you have a starting place, and then you can prove you can always step to the next number. So this is the method of proof, and it essentially is following the statement of the theorem, principle of mathematical induction. So we're trying to prove a statement of the form for all integers n bigger than or equal to a, the predicate p of n is true. Now in order to prove this statement, we have to perform two steps. Step 1 is called the basis step. We'll show that p of a is true. So a is some particular integer that represents the starting point for the induction. Step 2 is the inductive step. We're going to show that for all integers k bigger than or equal to a, if p of k is true, then p of k plus 1 is true. And now let me outline that a little more. So in order to perform this step, what we're going to do is suppose that p of k is true. K is any particular, but remember, arbitrarily chosen integer. And k has to be bigger than or equal to a. And this supposition is called the inductive hypothesis. Once we've made that supposition, then we want to show that p of k plus 1 is true. So keep in mind that k has to be arbitrarily chosen. You don't get to choose a value for k. So we're always going to have to use a variable in there. All right, now let's go back to our McNuggets problem, the one with the 3's and the 5's, and let's show that any amount greater than or equal to 8 can be purchased. Now what we'll do is we'll phrase it in a way to make the statement completely mathematical. We won't talk about McNuggets and all. Although if you want, you keep that in the background. So we'll state a theorem like this. For all integers n bigger than or equal to 8, n is equal to 3s plus 5t for some s and t in the whole numbers. So we use the whole numbers here because we want to allow for the possibility that s or t could be equal to 0. I guess if you're going to go back and think about the McNuggets again, there's a possibility that you might not purchase any boxes of 5 or you might not purchase any boxes of 3. Let's let p of n be the predicate. There exists s and t in the whole numbers such that n is equal to 3s plus 5t. All right, first we're going to show that p of 8 is true. Well, p of 8 is true because 8 can be written as 3 plus 5. Now that's easy. Now if you really want, you would say that 8 is equal to 3 times 1 plus 5 times 1. The 1 and the 1 tell you how many 3's and how many 5's to purchase. But when you're getting 8, you know how to do that. You just get 1 3 and 1 5 and add them together. Next, we're going to show that for any integers k bigger than or equal to 8, if p of k is true, then p of k plus 1 is true. So to do this, we suppose that p of k is true for a particular but arbitrarily chosen integer k that's bigger than or equal to 8. All right, so the way we're going to write that is we'll suppose that k is any integer satisfying k bigger than or equal to 8, so that k is equal to 3s plus 5t for some t and s in w. All right, now our goal is to show that p of k plus 1 is true. That is, so we need to show that k plus 1 can be written as 3s prime plus 5t prime for some s prime and t prime in w. So these are going to be different s primes and t primes. Once we have a way of expressing k, we need to alter that somehow to get a new expression for k plus 1. So we talked about how this is going to go. If we have some 5's, then we're going to exchange a 5 for 2 3's. All right, so that's our first case. We say, well, what if t is bigger than or equal to 1? That means that in the sum that makes up k, there is at least one 5. Now we can replace the 5 with 2 3's in order to get k plus 1. So we say, well, k plus 1, I know that k is equal to 3s plus 5t, we just have to tack on a 1. And now we're going to modify 1 so that 1 looks like 3 times 2 minus 5 times 1. Now you couldn't possibly argue with the fact that 1 is equal to 3 times 2 minus 5 times 1. The whole point is if that we rearrange this, that we get something that looks like this. So the idea is that what are we doing? We're removing one 5 and we're adding a couple of 3's. Now since s is a whole number, s plus 2 must be a whole number. And since t is a whole number and t is bigger than or equal to 1, t minus 1 is a whole number. So we have written k plus 1 as a sum of 3's and 5's. Now the second case is, what happens if there are no 5's? So that's what happens when t is equal to 0. Now we know that k is bigger than or equal to 8, so how many 3's do we have to have? Well, we'd have to have at least 3 of them, otherwise we wouldn't add up to at least 8. So now we can replace 3 3's with 2 5's. All right, so now what does the sum look like? So k plus 1 is equal to 3s plus 1. Why is that? That's because k has to be equal to 3s. Well, it's also equal to 3s plus 5t, but remember, we're operating into the case where t is equal to 0. So now we're going to do a similar sort of thing where we replace this 1 with 3 times negative 3 plus 5 times 2. What are we doing? We're removing 3 3's, we're adding in 2 5's. And now we reorganize it so that it looks like this. Now s is a whole number, and s is at least 3. That means s minus 3 is a whole number. So now we've written k plus 1 as a sum of 3's and 5's. You'll notice how many 5's are there? Well, now we've got 2 5's because we replaced 3 3's with 2 5's, and when we started we didn't have any 5's at all. So in either case, we have proved that k plus 1 can be written as a sum of 3's and 5's. So we've proved the basis step and the inductive step, and therefore, by the principle of mathematical induction, the original statement is true. Okay, that's all for now.